Good morning. Welcome to the PID Control Theory Lecture 4B. Today we'll be looking at an online simulation of tuning a PID controller. Firstly, I would like to give many thanks to Louis Lamas, the maker of this website. So this website is a nice and intuitive way that we can look at tuning a PID controller. So if you take a look at the simulator, what we have is three variables k, or this is kp, ki, which is the integral parameter, and then kd, which is the differential parameter. You also have this graph below over here. So we're first going to set everything to 0. So let's look at what these graphs mean. So this dotted blue one is a set point. This is the desired value we are trying to achieve. And you can see that it actually has the ideal response. You can see that there. Now PV, this pink line, this is the line we care about. This is the process variable, and that is what we are trying to watch. Now the output, which is the green line, which you obviously can't see here. Let's see if I play around. Now you can see this green line. That's actually the output of the controller. We are not exactly too worried about the output of the controller. We are worried about PV, which is the process variable. So if you remember how we tune a PID controller from the last lecture, remember that we have 5 main steps. So remember, step 1, put everything to 0. Well, specifically we want Ki and Kd to 0, but K is up. You might as well put Kp to 0 too. So that's step 1 complete. Now step 2 is bring Kp, or in the simulator K, up until it hits the set point or the overshoot hits the set point. So let's do that. Slowly bring K up. And now you can see this overshoot here. And it just about touches that set point. So that's how we can tell that K is okay, because that overshoot is touching the set point, our desired area. Okay, that's Kp complete and step 2 complete. Okay, now if you remember that what Ki is used for, the integral parameter. So the integral parameter is actually used to bring this offset over here in the steady state and bring it all the way up to the set point. So we are increasing Ki until the offset is removed. So let's do that. So Ki is typically a tiny variable, and we slowly increase it until that's about right. That looks about right. The offset is basically 0 over here because we have got that steady state to become close to the set point. Okay, now step 4. We actually want to smoothen this signal. So you can see there's an overshoot, there is a bit of oscillation there. We want to smoothen out those overshoot and oscillations. So to do that, we can actually increase Kd, or the differential parameter. So by gradually increasing Kd, you can see the overshoot actually goes down, the oscillations decrease, and overall the signal becomes smoother. Now you want to be careful how much you use Kd, because it actually acts erratically to high frequency noise. So if I shoot Kd all the way here, you can see the signal becomes quite jaggedy and it's not exactly smooth anymore. So you want to be careful with Kd. Now I think over here is perfectly fine at Kd equals around 15, yeah. But you still see there are some more corrections we can do to the signal, and that's step 5. Step 5 is do any fine tuning you need to do. So what fine tunings can we do? Well, firstly, you can see there's a bit of an overshoot and there's a bit of an offset. Can you see how the PV signal, once it overshoots, it actually takes a while to gradually get down to the set point. So what we can do here is reduce Ki. By reducing Ki, we bring this PV, or the pink signal, down to the set point. So let's do that. So we can reduce it. And so we have Ki equals 0.021. And you can see that the PV signal is actually practically bang on the set point. And this is a very nice looking signal. Now, again, you can still see there's a little bit of an overshoot there. And that overshoot may be acceptable to you, it may not. But if you want to remove this little overshoot, you want to remove the overshoot, given that there is no offsets left over in the settling time, we can actually reduce Kp a little bit. So to reduce Kp, by reducing Kp, we've reduced this overshoot. Now, you might look at that and say that's perfectly fine. To be honest, I think that's a perfectly fine signal. But if you want it to be even cleaner than that, You can reduce Ki because there's a very tiny there's a very tiny offset produced. So let's remove that. So we can take Ki down to 0.019, and now this entire signal is sat on the set point. That is really nice. We like that. Now, maybe KD is a bit too high. You can still see, if you have a careful eye, you can see there's a bit of a corner here. It looks like there's a bit of a sharper change there. So we can reduce KD to make it smoother. And so let's remove that offset though. And so by putting KD to equal 13.6, for example, we can remove that jaggediness if you've seen it, and practically the signal is perfect. I think I'm very happy with this signal. Now this website has generously given us some hints. So it says hint around K equals 2.5, Ki equals 0.02, and Kd equals 12 looks promising. Now you can see our variables here. They actually look somewhat similar to the hints, but let's try out the hints. So K equals 2.5, Ki equals 0.02, and Kd equals 12. Now, as you can see, the signal again is very good. Now, if you're careful and you can actually see a very tiny overshoot. Now, this overshoot is generally acceptable because it's very tiny, but perhaps you can't accept this overshoot. So if you want to reduce this overshoot, what you have to do is you can actually reduce KP a little bit to take this overshoot down. And now you see this overshoot is gone, but there's actually a very tiny offset that gradually reaches the set point. Now to reduce this offset, you simply reduce Ki a little bit. And so now you don't have any overshoot and you rise slightly slower, but your PV signal, your output signal stays at the set point. And this is very ideal. To be honest, I think the hints should have just been 2.2, 0.018, and 12. I think those three variables are perfect. Okay, that's the steps to tune a PID controller. That's finished. So in the next lecture, lecture 5, we will look at the different variations of the PID controller. Thank you. I hope to see you next time.